let me know. So I want to start with recalling what we were discussing yesterday. We look at the category of GK modules and GK. No, I mean, which we discussed last time, and I want to make two remarks because they came up in the discussion later. This category basically is just G modules and K naught modules with some compatibility condition, no other condition at all. And the reason for using this category to start with is because it has enough injective and projective objects. So you can start doing homological algebra on this category. The modules you are actually interested in are in much smaller category, but which have worse homological properties. Then we have this subcategory A GK naught of modules which were finitely generated and ZG finite. And I will discuss this in more detail in a moment. There are two remarks I forgot to stress. First of all, one remark which is critical is for development of Harishchandra's work is that if I take an irreducible unitary representation and apply this construction of K-naught finite vectors, which is in NG K-naught, then irreducible module, the irreducible unitary representation goes into irreducible GK module. I mean, the definitions of irreducibility are different. For unitary representations, this is that there are no non-trivial closed invariant subspaces. Here, definition of irreducibility is completely algebraic. So there are no non-trivial invariant subspaces. And the proof is based on the fact that K-naught finite vectors are analytic. So if you take an irreducible GK naught module, which comes, say, from unitary representation, and a GK naught module which comes from unitary representation, and look at it, if I take a submodule, sub GK naught module, I can close this subspace. And because this is a Hilbert subspace or Hilbert space representation, and because this is a closure of the space of analytic vectors, it's also, I can write a group action using Taylor series around identity, and the subspace is invariant and for each vector there is a neighborhood in the group, and this is inside, and then since neighborhoods generate a connected group, this gives us that our space is invariant under the group action. And it's closed, so if our original representation is irreducible, it must be everything. Now, so this means that our submodule of GK non-module of K finite vectors must be dense. But then, if you project it to one of isotypic components, then you get denseness of the projection in this space. And since Harishchandra proved that unitary irreducible representations are admissible, this is a finite dimensional subspace, and a dense subspace must be everything. So we see that corresponding GK naught module stays irreducible after this construction. And then, of course, such an irreducible object is automatically here because it's annihilated by a maximum ideal in the center, and also it's generated by one vector, the non-zero vector under the UOG action. So our irreducible objects, which come from irreducible unitary representations, irreducible in this category and therefore in here. So this contains all irreducible GK modules. Okay, so now let's observe what else we can say. Let's see if since these modules are finitely generated and every vector is a ZG finite, I can take my finitely many generators, generate the ZG invariant subspace, and it will stay finite dimensional. So there is a finite dimensional subspace U and so this is ZG invariant subspace such that V is U of G applied to U. And then since this tells us that annihilator of this U annihilates V. So any object in here is annihilated by an ideal of finite codimension in the center of the enveloping algebra. So now, since under the action of center, like say linear algebra, we can decompose our V in direct sum of generalized eigenspaces with respect to Z of G action. So this is, say, VI hat, where I is a maximal ideal from some finite set because of finite dimensionality. In the space of maximal ideals of the center. And this just means that there is some integer n such that Z to the n in I annihilates this subspace. So this is a primary component in the decomposition. So this is, of course, invariant under the action of U of G and of K. And so we can take, so I have a direct sum decomposition, and each of these pieces has a finite filtration such that all graded pieces, so this is essentially to a Jordan form, so there is a filtration of the I hat such that GR of the I hat is annihilated by maximal ideal I. And this tells us that actually we have, if we put this together, there is a finite filtration of an object here by GK submodules such that the graded pieces are in the category of, say, A. Let me introduce some notation. So let I be a maximal ideal in the center, as before. And I define U of I as U of G quotient by I, U of G. And then, we can say that the objects in these categories have finite filtrations, and the graded pieces are in a category of, that's denoted by A, U, I, A naught, where this means these are GK modules, which are finitely generated CG finite, and the action of enveloping algebra factors to this quotient. So, the theorem I mentioned last time follows that, so let me just annotate here, we claim of finite length follows from a theorem that modules in A UI K naught are of finite length. So, of course, this is nothing else than finitely generated modules for UI K naught. And we define this subcategory in an analogous way because the CG finiteness is absorbed in this condition. So there was a discussion last time about attribution of this theorem, and so I think it's fair to say that this is a result of Harishchandra, although his proof was quite different. So let me describe how he argued. If you analyze his papers, he shows that the objects in this category are admissible, so their K multiplicities are finite. If, in this case, you can argue like this: any irreducible object here will have Harishchandra character, the Brenda Prasad discussed in his lecture, and we are going to talk about this in more detail, I hope, in one of the following lectures. And Harishchandra proved that if we fix the action of the center act by a homomorphism corresponding to a maximal ideal, then the space of corresponding invariant eigendistributions is finite dimensional. Characters of different irreducible representations are linearly independent. So this implies that in this category there are only finitely many irreducible objects. So now, if you just look at decreasing filtration, such that quotients are irreducible, there are only finitely many choices. And if you would be able to create an infinite filtration, this would mean that some k-types has to appear with infinite multiplicity. And this would contradict admissibility. Because there are only finitely many choices, so the sub-quotient, irreducible sub-quotients have to repeat themselves, and this would force that the multiplicities cannot be finite. So this is Harish-Chandra's approach to this theorem. I want to push for another argument, which is just to advertise the use of D-modules for such things, and this is the next topic I want to discuss. But first, I want to mention Harish-Chandra's result about the space of maximal ideals in the center of the center of the animal algebra. So this was one of the deep results Harish-Chandra proved in, I think, a big paper about the structure of the enveloping algebra. So if you look at the center and you fix a Cartan subalgebra, in G, so in the Raghunathan's talk, this was just, his discussion started for compact, semi-simple groups. This was a complexification of the Lie algebra of the torus. You can define this motion in general. Then, if I take an element, say zeta, in the center, then there exists a unique element, gamma zeta, in the enveloping algebra of C, sorry. I usually denote Cartan subalgebra by H, but I will use H for something else in a moment. So C, such that this is contained in N UG, and I have to tell what N is. With this, I look at the root system of G with respect to C. Say, and I pick an ordering. I can run that install R plus, and I consider the Lie algebra N, this is by N, which is the sum of root subspaces G alpha, and alpha goes over the set of positive roots, R plus. This is an important Lie algebra, and it's an easy exercise to prove that this stable position exists, and this gives you the map gamma from the center of 0G into the enveloping algebra of C And then you can look at here at evaluation at the point lambda plus rho. So rho is half sum of positive roots in our root system R. So evaluating, I look at this enveloping algebra is the same as this symmetric algebra. So taking a linear form in the dual of C, I can evaluate this and I get homomorphism from C into complex numbers, which extends to the enveloping algebra. And I can look at this homomorphism of the center and the kernel, so of this gamma inverse, I call the kernel of this, say I lambda. So gamma of I lambda is an element of the space of maximal ideals of Z of G. And Harishchandra proved, so this is the...
What is that map from the Euclidean interpretation?
Which one?
The one from the Euclidean about the carbon roots. What is that map?
I mean, this is the same as the symmetric algebra of H. Yeah. So if I have a linear form on H, it extends to the homomorphism of this the complex numbers.
Also, that lambda also should be in the dual, right?
Oh, lambda is just arbitrary. Yeah, I see. Lambda is an arbitrary element of C star.
Lambda is always C above. That's a completely different interpretation. Lambda is also in C star.
Yeah, rho is oh. Okay. Sorry. Thank you. So the main point, like, if you are not familiar with this rho shifts, just ignore them for the moment. The point is that this map from lambda to maximal ideals is not by a bijection, but we have a Weil group W of R, which is generated by reflections with respect to roots in R, and gamma inverse of I lambda is equal to gamma inverse of I mu if and only if lambda and mu are conjugated by some element of the Weil group. So Harishchandra's theorem says that the space, the set of maximal ideal, so Z of G, is in one-to-one correspondence with the W orbits in H star, in C star. Sorry. Divide C star, divided by. So this is the fundamental result about structure of the set.
So
What is I lambda? Oh, let's can you say it louder?
Yeah, so just can you repeat what is this I lambda in this complete diagram?
What is this I lambda? I lambda is the maximal ideal defined by lambda plus rho. All, say, this is the kernel of the homomorphism given by lambda plus rho. So, I mean, now this parameterization will become important because I have to start now talking about geometry. So, what we have here is this n, and we have a Cartan C. If I look at C direct sum with n, this is a solvable Lie subalgebra of G. And it's maximal solvable, and all maximal solvable subalgebras of G are called Borel subalgebras. And they form the smooth algebraic variety, which is called the flag variety, of G. So this is an algebraic, all Borel subalgebras are conjugated by the action of the, say, int of G, if you want, this algebraic group. So this flag variety is a quotient of this group by the Borel subgroup corresponding to particular Borel subalgebras. So it's a smooth projective variety. Now I need some notation before I can formulate the basic objects construction. So first of all, I can look at the vector bundle or flag variety of all a trivial vector bundle corresponding to G. Then inside it, I can look at the subbundle, which consists of pairs X and B of X, where B of X is the Borel subalgebra corresponding to the point X in flag variety X. I mean, the points are Borel subalgebras, but it's kind of silly notation to denote Borel subalgebra by X. And this is a homogeneous subbundle of this. And then our N in a Borel subalgebra is equal to the commutator of E itself. And this is our E. And inside this, so let me call this vector bundle B. And inside it, I can construct a subbundle which consists of, say, x's and n of x's, where n of x is a commutator of v of x. This is again a homogeneous vector subbundle of this trivial bundle. And if you look carefully at conjugacy theorems, then you see that B mod n is a trivial bundle over X. So, as a say G homogeneous bundle, so is
So this Dx is not a point, right? It is just a lot of points. Say suppose the Borel subalgebra.
Borel subalgebra is one point in the flag variety.
Yeah, but in G.
No, in G, yeah, I'm looking at all the, I mean, this is just a fiber in the vector. Yes. So, the point is, I mean, this is kind of weird construction at a first moment, but you will see what is the point in a second. This quotient is a trivial vector bundle, so since X is projective, so the global sections of the quotient, so let's call it script H, are just constant sections, and space of those is finite dimensional, and we call it H, and call this abstract Cartan algebra. Okay, so let me explain why we are doing this. I mean, this was the part of the construction by Valenson and Bernstein.
And that script, then what is that?
B mod n is the quotient.
What is N?
N is the vector bundle where the fibers are the important radicals of these Borels. So the commutators of B of X with B of X. This is the
So this is the
yeah, this is just the subbundle of this bundle. So, if we consider a point in flag variety X, this determines a Borel subalgebra. In this Borel subalgebra, we can pick a Cartan. And of course, this is not canonical, but all Cartans conjugates by the elements of the group corresponding to n of x. And this will play the critical role. So I can look at the map C into B of x, and then I can project to B of x mod n of x, and this is a fiber of this trivial vector bundle, so there is a constant section of this vector bundle passing through this point, so there is a map into our abstract Cartan algebra. So fixing the point x gives me a canonical map from some Cartan subalgebra in B of x into abstract Cartan subalgebra algebra, and then I have a dual map which goes from H star into C star, which is called specialization. So the point is that we don't want to fix a base point in the flag variety, because this would make the notation extremely complicated. So we want, for example, that line bundles on the flag variety are parameterized by weights on H. So, any questions?
The cartons are available, that is inside one borel.
Yes.
But how do you take, like, if you change the borel, the cartons are available.
Then you get a different specialization. This is a great question, because you will see in a moment in the construction, this will give you a different function corresponding to this. This is exactly the reason why we need to introduce all of these weird notation.
In this flag variety, you're only considering the full flag by looking at this.
Yeah, only full flag variety. I mean, you will see when I state some theorems, these theorems hold by miracle only for full flag variety. Okay, so let me so if I take a weight of my abstract cartan and I fix a point in the flag variety, this weight will define a weight on the cartan C. To this weight on cartan subalgebra C, we can extend it to a representation of the Borel. We can construct the line bundle. Are you going to talk about Borel veil at all? No. So, I mean, if I look at this line bundle, this is a line bundle on a flag variety X. And locally, it looks like regular functions on open sets. So it's natural to consider notion of differential operators with, say, algebraic coefficients which acting on this line bundle. So for, like, say, mu, I can look, I denote by O mu this sheaf of sections of the homogeneous corresponding to the rate. And I can look at the I don't remember when I started, so I don't know when
Yeah,
I
you
have
have
to
time.
stop.
You have time till at least 20 minutes.
So I still have 20 minutes?
Yes.
Oh, okay, great. Great. So I can look at sheaf of differential operators. So what are differential operators in this case? So I think at the tutoring session, we can discuss, say, people are interested more about differential operators, I will lie a lot here. But basically, locally, we say what the section is, and C-linear endomorphism of this line bundle is a differential operator if for any n tuple, n plus tuple, n plus 1 tuple of regular functions f0, f1 up to fn, if I take the iterated commutator or my endomorphism T in these functions, this gets me to 0. Then we say that such T is a differential operator on O mu of degree less than or equal to n. So differential operators have a natural filtration and they define a sheaf of this. If O mu is just correspond to weight 0, so this is sheaf of regular functions on X, and these are ordinary differential operators on X.
How you are constructing this before that the line bundle corresponding to a weight?
Oh, this is because the weight defines the representation of the stabilizer of at that point. So if you have a representation of the stabilizer, then there is a standard construction of homogeneous vector bundle attached to this element. Again, this is something which should be discussed on tutoring. So now what as to the following definition, that the twisted twisted sheaf of differential operators. I mean, for example, these line bundles can be viewed as twisted sheaves of regular functions. I have regular functions on open sets, and then the glue is different. And here, I define twisted sheaf of differential operators as a sheaf of sheaf A of algebras such that for any point in our variety there is an open set. This A comes with a map IA from OX into A, such that any point has an open neighborhood U, such that OU A restricted to U, and OU of course maps into differential operators D and U, so that there is an isomorphism such that this diagram produces. So locally, our sheaf of algebra looks as a sheaf of differential operators, and these are these twisted sheaves of differential operators. What I described here, that to any weight we attach a sheaf of twisted differential operators on the flag graph. This is like, so now if you think about this, for some time, you see that the gluing condition for line bundles is much stronger condition than gluing differential operators. And there are more twisted sheaves than of differential operators than differential operators of line bundles. So, what Beilinson and Bernstein constructed is the following. For any lambda in H star, they constructed a twisted sheaf of differential operators. D lambda on X, which comes with a natural homomorphism of the enveloping algebra into global sections of D lambda on X. I mean, in this construction here, of course, I have a homogeneous line bundle, so I can differentiate the action of the group of this homogeneous line bundle, and I get the map from Lie algebra into first order differential operators on this homogeneous line bundle, and then I extend it to the map of the enveloping algebra into a global section of the sheaf of differential operators. But this can be done for all lambdas in H star, not only weights. So there is this twisted sheaf, and there is again mysterious row shift. So D lambda is, if lambda is a weight, is the sheaf of differential operators on O lambda plus rho. There is again the rho shift, and
Excuse me,
yeah.
what is the U over here?
U is, you look at a flag variety, you pick a point, there exists a neighborhood where your restriction of the sheaf to U is isomorphic to differential operators on U, and this isomorphism commutes with the inclusion of the regular functions.
I mean, there's a very specific choice of giving what for this isomorphism to work, right? Or would this isomorphism with the differential operators on U?
I mean, of course, this arrow here is just mapping functions into zero coefficient differential operators. So local isomorphism tells you what has to be happening here. Okay, so now we get to the, I mean, this looks like the margin theory and has no connection with representation theory, but then I have to tell you the so there is a theorem due to Beilinson, Bernstein, which says the following, that first when I fix lambda, this lambda determines the Weyl group orbit of lambda, which I denote by theta. And this theta determines the maximal ideal in the center of the enveloping algebra. So I will denote u theta as this algebra corresponding to the maximal ideal attached to theta. So the first statement is that this arrow introduces an isomorphism of u theta with gamma x lambda. So we know what are the global twisted differential operators. The second statement is that higher cohomologies of x d lambda is 0 for all these. What did we accomplish? We accomplished to construct a geometric model of this quotient of the enveloping algebra. A sheaf on some variety such that its global sections are isomorphic to this sheaf. And then this, if you ever studied Sayre's paper of cohomology of coherent sheaves, then you see more or less what one should do in the next step. We look at the category of mu theta modules and the category of lambda modules, which are quasi-coherent as OX modules. OX sits inside this, so this is perfectly well defined. If I take global sections of any sheaf here, these global sections are module over global sections of d lambda. So this is u theta module. So I get a functor of global sections x, which goes into this direction. On the other hand, I can do the following. If I have a module here, okay, let me write it here. I can take d lambda, tensor it over global sections of d lambda, which are nothing else than u theta, b, and this is d lambda of b. This is localization of b at lambda. So now we get to your question. You see that you can localize a representation of your u theta at order of Weyl group places, and you will get different reincarnation of your module. And this is extremely useful, the theory. I mean, everything I'm saying maybe looks very abstract, but also the proof is not technically complicated. So, if you look at Sayre's paper, this is described in a extremely beautiful way, or in Hartshorn book, I don't find it as beautiful as Sarah's paper. So you know how to proceed. At least you can hope that. So I think I have a few more minutes.
Yeah, yes. 5 more minutes.
5. Okay, great. I'll finish 5 minutes. So these two functors, if you look at them, they are adjoint to each other. So we have an adjoint pair. So if I look at homomorphism in a category of the lambda modules, from the localization of some module B into some module, the lambda module U, this is the same as on U theta B global sections of so now I will make a precise statement next time, but let me just state it so because I want to explain what's going on. There are two results which are completely analogous to Cartan's theorem A and B, or corresponding results in Sayre's paper for cohomology of sheaves on affine varieties. That under so this is theorem A. So under some condition, which I will specifically define, higher on lambda H E X of V equals 0, or so higher cohomologies vanish for these in NQC. This implies that the functor, of course, that the functor gamma is exact under these conditions. And under slightly stronger conditions, we have to add regularity of lambda. We have theorem B. So V in NQC d lambda is generated by global sections. Okay, so now the homework is look at Sayre's paper and his proof and use A and B to prove the theorem that under these conditions, these two functors are equivalences of categories. So basically the strategy is you want to solve the problem here, say about representation theory. You localize this and reduce the problem on about the lambda modules. This problem is sometimes simpler because locally the modules look like modules over sheaf of differential operators. They're all the same. We don't have all the possible different semi-simple E algebras. So in a way, this is an easier problem, and then we have to figure out what happens with law. next time, if we are localizing GK modules, then there is an action of the group here, and there is an action of the group of this. So our localizations are not only modules of a sheaf of differential operators, but there is also the action of the group. And this fact, and a simple geometric fact we will discuss next time, will imply that the D modules which we get here by localizing our, say, what I will call Harishchandra modules, so these D modules I will call Harishchandra sheaves. So these Harishchandra sheaves are so-called holonomic D modules. And holonomic D modules, for very simple reasons, I require to prove our finite length. And this will prove our theorem I mentioned at the beginning. So this is the flow chart of the next talk tomorrow. And then if you are interested in more details about these algebraic things and D modules, come to the tutoring session and we can chat about this. Okay, so.